Thank you very much for having me. Today I wanted to share with you some results that were published here at the APS last year with my thesis advisor, Professor Angel Rivas. And our main motivation for this work was the following. We know that controlling non-Markovianity is challenging since it usually requires environmental control. But we also know that in the multipartite case, the time evolution of some part may depend on the time evolution of some other through correlations. So we wonder whether the memory effects will be sensitive to these correlations, because in that case, it seems that it will be possible to find a system that in which you can change the memory effects by changing some internal parameter to the system, so no reservoir control needed. And this will be our goal, to find a system that displays this sort of behavior as a proof of concept. But before we can do that, we first need to specify what we mean by non-Markovianity, and our starting point was the RHP measure, which basically assesses deviation from CP divisibility. So if the dynamics is not CP divisible at some time t, this function g of t will be positive, otherwise it will be zero and not contribute to the measure. And this has the nice property that it's additive under tensor products, so it seems appropriate for our purposes in the multipartite case. But along the course of our research, we found two main disadvantages. First, and actually both of these can be nicely illustrated with a well-known example of a single two-level atom inside the resonant QED cavity. And the cavity starts in the vacuum state, and losses are modeled with a Lorentzian spectral density, as usual. In interaction, Hamiltonian preserves the number of excitations. So in this case, you can solve the dynamics of the atom, which is the open system, with pen and paper, and you can calculate the function g of t likewise. And we can see that it has two features. First, it has simple poles that cannot be integrated, so the measure is not well defined. And even if this was not the case, the function g of t is periodic while the dynamics is relaxing. So the measure seems to be insensitive to relaxation. So, and we can see that with this plot of the fidelity between the Troy matrix at time t and the Troy matrix at infinity. So in order to correct these things, we proposed a modification of the measure. First, we introduce a weight function that would approach zero at a similar rate as the dynamics relaxes. And this can be done in many ways, but we chose this in terms of the fidelity again. We corrected the divergences with this square root followed by square procedure. And last but not least, since we cannot simulate infinite time in our computers, we replace the infinities in these expressions with some finite simulation time. So having answered this preliminary question, we can go into the model. And what we did was consider a minimal extension of the previous example. So we just went from a single atom to just two. And this seems innocent, but it isn't. So in order to make things a bit more tractable, we restricted ourselves to just 0 and 1 initial excitations. So our hope will be that we can modify the memory effects by changing the separation between the two-level atoms. So we show in the paper that in this case you can solve the exact reduced dynamics if you know these two functions that can be solved for with numerically exact methods. And furthermore, we show that the dynamic satisfies an exact master equation with time-dependent decay rates. And these decay rates depend on these two functions, R as well. So this actually helps a lot in calculating the measure, and we see that the function g of t now goes with the negative part of the decay rate, so a negative decay rate indicates memory effects. So with this, we can already start tackling our initial question. So we found this intermediate regime for intermediate spectral widths, in which for distant atoms you get two positive decay rates, so Markovian dynamics. But as you bring the atoms closer together, one of them dips below the x-axis, so you get a finite transition from Markovian to non-Markovian dynamics at a finite non-zero separation. So, let's wait for the video to end. So besides this critical regime, we found two others too that we called Markovian and non-Markovian, since in those cases you cannot induce a transition by changing the separation. But in the non-Markovian case, we still see some sensitivity to the distance between the atoms. In fact, we can see that there seems to be an optimal separation that maximizes the measure. And I do not have time to get into the details here, but This is due to three facts: the fact that we introduced the weight function in the measure, the fact that we are considering finite simulation times, and more crucially, the fact that there is a two-dimensional decoherence-free subspace at exactly zero separation that is spanned by the ground state and the singlet. So in order to remove the finite simulation time out of this phenomenon, we considered increasing simulation times, and we observed that the distance that maximizes the measure actually approaches zero. But actually it approaches a discontinuous curve, again, due to the two-dimensional decoherence-free subspace at d equals zero. And actually we can calculate the limit from the right analytically, and it's done in an appendix in the paper. And then this is due to the breaking of asymmetry in the interaction term with the exchange symmetry of the position vector of the atoms. So do not have time for much more. So in summary, we introduce a computable non-Markovianity quantifier that is appropriate for the multipartite case and that has appropriate asymptotic behavior. We solve the dynamics exactly for two-level atoms in a cavity in the 0 and 1 initial excitation subspace. And we observe that indeed memory effects can be sensitive to some internal parameter, in this case, the separation between the atoms. And we also observe some sort of critical phenomena in the form of a Markovian to non-Markovian transition at a finite distance in some regimes and a discontinuity in the limit of infinitely closed atoms due to the formation of a decoherence-free subspace. So thank you very much for your attention. So I'll be happy to answer your questions. And if you want more information, please scan the QR code. Thank you.
Pretty quick.
Yeah, I mean,
So Ignacio was speeding up, so we have time for maybe more than a couple questions this time. So yeah, please.
I see in your title and here the conclusion you're talking about multipartite, but I see you're talking here about only two atoms, right?
Yes.
So it's bipartite. Did I miss it?
Bipartite, but the point is that the measure that we introduce is not limited to just two-part systems. I mean, the measure should indeed be able to work for multipartite systems.
Okay. So, but what you presented here is only for the case?
Only for two. I mean, in the paper, there's one more case in which we solve the dynamics for n atoms at zero separation. And we also observe a critical transition from Markovian to non-Markovian dynamics with a number of atoms. So there's a critical value for the number of atoms above which you get the transition no matter what the environmental parameters.
I can ask another. So another question is about how the distance takes you from Markovianity to non-Markovianity.
Like, how does it happen?
Yeah. So
I mean,
what happens physically there?
My intuition is the following. I mean, you can solve the dynamics for infinitely separated atoms and you get basically the one atom case because they cannot see each other. And when you have both in the same position, you get the usual superradiant dynamics, right? So there seems to be some enhancement when the dynamics get below some distance, like there's some coherent dynamics happening. So both atoms start to behave coherently and interact with the field more strongly, like in superradiance.
Hi. I'm just curious to know, so what if you have n two-level systems, and let's say their parameters are distributed according to some random distribution,
yeah,
and you're periodically driving it using Floquet, but you also have many-body interactions which are distance-dependent. Do you expect to see the non-Markovianity enhanced, or is it the interplay between the drive and the interaction will suppress it?
I have no idea. I mean, those are too many variables introduced at once for me. Sorry.
Okay, let's see one hand here, one there.
Thanks for the talk. I wanted to ask about your the exact master equation you derive.
Sure.
You said you have a Lorentzian spectral density, and so is this related to like a reaction coordinate or pseudomode technique for a Lorentzian spectral density, or is there some other technique for this master equation?
I mean, we just we propose the Schrodinger equation, the exact Schrodinger equation for the whole system of the cavity and the two atoms. we trace out the degrees of freedom of the cavity, and we find the reduced dynamics. And from then, we find the reduced density matrix, we take time derivative, and we identify terms, and we get the exact master equation in which these decay rates are independent of initial conditions. So they're like true functions, and it is actually the exact master equation. So let me get to that. The transitions make it harder, but we'll get there. That's actually easier. Yeah, so this is just the same procedure. You get exactly this, just by identifying terms and working in the appropriate basis.
I have a question. How do you define the Markovianity and non-Markovianity here?
Yeah, the non-Markovianity is defined as deviations from CP divisibility. So if the dynamics is not CP divisible, the trace norm of the Choi matrix will be greater than 1, since the Choi matrix is a 1-to-1 correspondence with the dynamics, and this function g of t will be 0. So this is what we mean by non-Markovianity, deviations from CP divisibility. There are some other possible definitions for non-Markovianity, but we chose this one.
Okay, got it. Thanks.
Okay, with that, let's thank Ignacio again.